First of all, thank you to the organizers for the opportunity to present this work at the Probability and Statistic Days. My name is Stefan Tappe from the University of Freiburg. I'm going to speak about joint work with Thorsten Schmidt and Wai-Jun Yu. The title of the talk is Infinite Dimensional Affine Processes. We will regard such processes in Hilbert spaces, or precisely on the canonical state space. So we have a separable Hilbert space, we fix an orthonormal basis, and then our state space is a cone of this type. The first component is a cone generated by this part of the orthonormal basis, and the second component is simply the linear space generated by this part of the orthonormal basis. We will regard affine processes as solutions to stochastic differential equations. So here we have such an equation. This is a usual setting in infinite dimension. This mu, this is a drift. So of course, everything is now defined on the canonical state space that we have defined on the previous slide. And the sigma, this takes its values in the space of Hilbert-Schmidt operators. So this W here, this is a driving Wiener process. It may have its values in another separable Hilbert space. And here we define this space to 0, showing up here. This is a usual setting in infinite dimension. And we also introduce the dispersion function S, and this will simply give us the quadratic variation of a solution to this SDE, provided it exists. At the moment, there are no further assumptions about the coefficients. When we speak about affine processes, we also need an affine structure, and you see this on the slide. So the drift is this affine structure, and the dispersion function that we have introduced also has an affine structure, as you see here. But we will also need that solutions of the SDE do not leave the state space. So here's again the state space, just to recall, and we need these admissibility conditions. These are geometric conditions, so the drift must be inward pointing. So if we are at a boundary point, which means this inner product here is 0, then this inner product here must be non-negative. This is the inward pointing property. And also we need that the volatility is parallel to the boundary. So if we are at a boundary point, as we see here, then this inner product here must be 0. This is a parallel property. So this will ensure that we do not leave the canonical state space. And now let's go back to this stochastic differential equation. So now we see that we can really speak about an affine SDE, and now we are looking for solutions. It's not so easy because we are in infinite dimension, and also the volatility behaves typically like a square root. But we can nevertheless get solutions if we start in a slightly smaller state space. And this is what we will see on this slide here, where we introduce a so-called retracted subspace with compact embedding. So the compact embedding is particularly important. And it will be given as follows. Recall first that our Hilbert space has a direct sum decomposition into two components, and we will only change the first component a bit. So the second remains unchanged. What we do here, we define a compact linear operator here, and we do this as follows. We define these two sequences here, and then there exists another sequence U such that this quotient here is an L2 sequence. One can show this. And by means of the orthonormal basis in this sequence here, we can define a compact linear operator, and then we consider the image of this compact linear operator. And this is a subspace which is compactly embedded in the first component of the Hilbert space. So, and then we define a new set of initial conditions, and slightly smaller, because now we in fact take this image here, and the second component is the same. So, and when we consider initial values from this smaller set, then we will get the existence of solutions, but we also need some further additional conditions which are in this slide. So they can all be checked in concrete examples. Let's go through it. So the first is an assumption on the Wiener process. The state space of the Wiener process should simply be equal to the state space H. And we also impose that the covariance operator has a diagonal structure along the orthonormal basis. For any x, this operator here should be self-adjoint. So, and if we consider these sequences defined on the previous slide, then this quotient here should be an L2 sequence. Concerning the drift, so the first part should simply belong to this smaller set of initial conditions that we have just introduced here by means of the compact embedding. And concerning the linear operator, so if we restrict this to the first component of the Hilbert space, we need this commutativity here and also that this series here converges. So these are a couple of assumptions, but as I said, for examples, they can all be checked. And under these conditions, we have the existence and uniqueness results that you see here. Just recall our affine SDE, that X denotes the canonical state space and that we have a slightly smaller set for the initial conditions. So under the assumptions that we have presented on the previous slides, then our stochastic differential equation, our affine SDE, has a unique strong solution for starting points in x0 set here. So this is our result, and rather than going into the proof, let me present some examples, two examples. The first is an example of Cox Ingersoll-Rass type. So here, our state space is simply the cone generated by the orthonormal basis. We don't have an additional linear space that we attach here. And then consider the dispersion function. It must have this linear structure here, and 0 is simply equal to 0, and capital N has this structure here, and this is why we speak of Cox Ingersoll-Rass type. What is important that this sequence lambda here is an L2 sequence. So then again, we can define the retracted subspace as before, and then we define the affine mapping. So the first component must belong to this smaller set of initial conditions. And concerning this operator here, we assume this structure here along the orthonormal basis diagonal structure, and this row must be an L1 sequence. Then we can check that all the assumptions of our theorem are satisfied, and we get the existence of unique solutions. Another example is as follows. So here we have the general canonical state space, and then the dispersion function with this linear structure is as follows. N0 satisfies this condition here, which means that the admissibility conditions that we have seen are satisfied, and the capital N has this structure here. Again, we consider the orthonormal basis, and we have now two sequences here satisfying certain regularity conditions, as you see here in this tau. This is simply an order-preserving bijection between these two index sets. So then again, we define the retracted subspace and consider the affine mapping mu, the drift. M0 again should belong to the smaller space of initial conditions. And if we consider capital M, it has this structure here. So Mj, the second component here, can simply be any linear operator. And this first component here is just as for the previous example. It has this diagonal structure along the orthonormal basis, and again, rho must be an L1 sequence. So then all the assumptions that we have seen can be checked again, and as a consequence, again, for the second examples, we get the existence of unique strong solutions. So this is all. This concludes the presentation. So what I have showed you is part of this joint paper here with Thorsten Schmidt and Baijun Yu. And on this slide, you can also see some related references. Thank you very much for listening to my video, and I'm looking forward to your questions at the live discussions.